So I promised that today we would enter the realm of learning, and today I will be a little bit less detailed than in the past few weeks. I mainly want you to take away the ideas, and some of you will know some of these things, so I will be a bit more superficial than I have been, but please do ask, please do stop me when something has been unclear, okay? So today I want to show you many pictures. The best thing will be for you to just take very rough notes, and then in particular remember, the title in first order if you want to look up one of these papers for yourself. So I want to introduce today a very versatile pipeline, namely to use filters that the human decides are probably useful to bring out something in your image that you would like to distinguish from the rest, and to then use a classifier. And I will show you what this looks like if you do this interactively. Did I show this at the beginning of the semester, by the way? I did? Okay. I will do it again a bit more slowly this time. So it's the same data that you previously saw, some super high resolution electron microscopic image of the brain. This is data courtesy of Graham Knott at EPFL. And we want to partition this volume into all its constituent neural processes. And as a first step towards this goal, we want to distinguish the different entities in the image. And so far nothing has happened. I've only loaded the data. We are looking here at 3 ISO views. I now need to select a few features. And at first, I am only going to select the color, which in this case just means raw intensity, at the smallest possible standard deviation. And then I can create as many classes as I want. And now I will, because I'm only using the gray value in each pixel, I'm essentially going to learn a threshold. Yeah, so I'm going to paint this membrane in red and the cytoplasm in green. And then there are some elongated structures that I'm interested in. Maybe I should switch to 3D to make sure I'm catching these. Yeah, so you see the crosshair, it shows me the same thing in each picture. So we have some elongated structure here. I will try and paint that in a different color and see what that gives. Okay, and then now I've given a few annotations. You've seen me paint these things, and then I can train a classifier. The classifier, what it sees is for the pixels that I did annotate, like the ones here, it knows that these pixels are the blue class, and it knows the gray value for these blue pixels. And somewhere else, I've forgotten where exactly, I painted 2 other classes, and the classifier knows the gray value, and that this is there it is, the red and the green class respectively. Okay, and now given this training data, it tries to learn a rule, it tries to learn a rule, and it tries to infer what class the pixels that I did not mark, what class they likely belong to. And well, it does something. It clearly, you know, mixes up the blue and the red class, and I have not tried it before, so I don't know if this will work at all. But, you know, I can try and refine this a little. I'm giving a few extra labels here, and then I see the classifier, you know, well, trying to follow these instructions, and it struggles a little bit. Yeah? So this is a very noisy prediction that I'm getting here. All right. Now I can try and add more informative features. So I'm going back to this feature dialog, and this time I am selecting, you know, let's say a couple of different scales of these gray values, and I'm also computing so-called texture features. And this will be something, the texture features are something that we know from last time. Yeah? So when I said I want to compute the color at different scales, these are the images that I created. So it's always the same image, just, you know, smooth with the Gaussians of increasing standard deviation. And then at the end of last time, we looked at the structure tensor, and here you see a coding of the magnitude of the first values. What we see here is red and green, but we know that they are sorted. So the first eigenvalue is always, can be no less than the second. So we should see no regions that are just green. We should at most see a mixture between red and green. The thing is that here the red and green and blue channel, they have been amalgamated into a color image, and you see different scales have been used here. So the first eigenvalue actually has values from 0 to 404, and the second one has values from 0 to 21, and the third only has values from 0 to 7. Yeah? So if I did use the same color scale here throughout, then I would see, you know, mainly red, because this is always the dominant eigenvalue, and then, you know, there will be a few hints of yellowish, where there's also some green elsewhere. Okay, but to visualize it more clearly, okay, I've taken the automatic range here. So this is what the raw data looks like to the structure tensor. I'm not using the directions of these eigenvectors, I'm only using the eigenvalues. And then there is the Hessian of Gaussian. What we do there is that we compute a matrix of second derivatives. So remember, for the structure tensor, we had the following. We had the first derivative squared, and we had the products of the first derivatives, and we had the second derivative, we had the first derivative in the other direction squared. This was the structure tensor. And then this thing was smoothed over a local neighborhood. And for the Hessian, we now use this, we use the second derivative. Yeah? So this would be gxx, gxy, gyx, which is the same thing as that, and gyy. And then this is again smoothed over local neighborhood and is again diagonalized. And the eigenvalues of this is what we're looking at in this false color plot here. And when I'm showing you here. Okay, now let's go back to this image. I'm not adding any labels, but I'm now training the classifier again. This time using these, using the new features. Okay, so it's the very same labels that you've seen before, but using a richer set of features. And if you remember, you know, the previous classification looked extremely noisy. This one here, you know, looks much smoother already. This is partly a consequence because the classifier now gets to see not just the image, but also smoothed versions thereof. you also see that the classifier still has a really hard time trying to figure out, what I mean by red class versus blue class. Both are dark, both are elongated structures. The thing is that the red class here is locally two-dimensional. This is a surface, whereas what I indicated in blue was at a big scale locally one-dimensional. So this was a tube in 3D space. And if I use a structure tensor with a sufficiently large scale, I might be able to make the distinction between the two. I'm giving this one more shot, so I'm now going to compute a structure tensor with a much bigger scale. Well, let's go all the way to 10, and let's look at this. So let me pretend that, so this is still computing now, let me pretend that the predictions are getting better, but in any case we can agree the predictions are different, okay, using the different features that I have selected. So let me show you how these features have been concatenated. I used the raw image, which I'm showing here as 2D, even though in fact this was 3D. And now I have concatenated all these different feature images. So maybe this was the Gaussian with the sigma of 0.3, and this was a Gaussian with the sigma of 0.7, and this was a Gaussian with the sigma of 1. And then I had, for example, the first eigenvalue of the structure tensor at a given scale, and then the second eigenvalue of the structure tensor at a given scale, and so on. So previously I had for a pixel just a single measurement, its gray value, and now I have this entire series of measurements for every pixel. And this series of measurements, they encode something about the local neighborhood. So taken together, they tell me a little bit what this local neighborhood looks like. All right, and so we see that the features that I did pick, they have been clearly able to distinguish cytoplasm from membrane and mitochondria, but the blue and the red class, I think the blue class, that was an example of an endoplasmatic reticulum, which I annotated here, it has a hard time discriminating the red from the blue class given those features that are available to the classifier. So the classifier does not see the image as a whole the way we do. What the classifier sees is the gray value at the pixel, and then these other features that you remember were computed with a standard deviation of something like 3 or so. So effectively, I get information from let's say a 9x9 neighborhood around each pixel in these numbers. Okay. So in a machine learning class, a typical picture that would be drawn is the following. I have a vector of training labels, and then I have a matrix of features or observations. So for example, if I have 17 features, then I would have 17 columns here. Each row corresponds to one training example. My training labels here, they were the red, the green, and the blue class. And I'm trying to learn this mapping here from features to labels, such that once I have learned a good mapping, I can make automated predictions reliably. And in fact, in this task of partitioning this brain data, this is the first step that we're doing. We're just figuring out what is membrane and what is non-membrane, and then we do a whole lot of other things on top. But that is the beginning of the pipeline. Okay. This basic scheme of computing features locally, features that were designed by a human, and then training a classifier to make local predictions has been extremely successful. And it's not been, so that the principle of this has been known for a long time, but realistically, it has only been used since 2005 or so. And previously, people in computer vision didn't really train these local classifiers. Rather, they tried to, somehow create sophisticated filters that, when thresholded, already give the desired output. Among the many success stories, I've here picked a single paper. This is the technology behind the Kinect sensor that some of you may have at home. So this is a device sitting on top of your TV box, and it recognizes your pose and allows you to somehow play games and so on. And it's extremely simple. So the sensor in itself, it has the sensor is a primitive range sensor. So it gives you, I believe, a color image. It certainly gives you a low resolution depth image. And in this paper, the authors then from the depth image, and I'm not sure if they even use the color images at all, they compute a number of features for every pixel. They then make this pixel-wise prediction. In this case, they had not used just red, blue, and green, but many more classes, as you see here. There was one class for shoulder, one class for upper arm, one class for elbow, one class for fingertips, one class for head, and so on. And you see that the predictions here are somewhat noisy. So shown for every pixel is the winning class, the most likely class in that pixel. And afterwards, they simply take essentially a robust mean of all the pixels of a given color, and they end up with the dots that you see on the right. So let's say all the shoulder pixels are aggregated into this single coordinate here, or the elbow pixels are aggregated into that coordinate, and so on. And from this set of points, the pose is then actually inferred, and the game is being steered. Okay, any questions so far? So this is the basic setup. Compute local features and make local predictions. And next, I want to give you a few more details on the kinds of features that you could compute and on the kind of classifiers that people use. Yeah? So kinds of features, what I showed you just now in this interactive demonstration were a couple of linear filters. So there were Gaussians at a few scales, and you can also select difference of Gaussians and so on. In fact, many people just like to use differences between pixel values. So let's say if we want to make a prediction at this pixel, they will ask what is the gray value difference between this pixel and that pixel, which is some distance off. Or in the case of the depth image, this is one of the features that the people from Microsoft used. They asked, what is the depth in this pixel minus the depth in that pixel, which is a couple of units away. And this also is just a linear filter. Yeah? This is, if you think of it, if you think of it as a filter mask, this would have a +1 here, a -1 there, and then zeros for all the other pixels. This is not how you would implement it. Yeah, you would not use a convolution to do this. You would just really look up the pixel value, but you can formulate it as a convolution with a linear filter. You can use smoothing filters, high-pass filters, etc. Okay. Then there are nonlinear filter banks. I've shown you two examples, the structure tensor and the eigenvalues of the Hessian. There is a large class of filters that we have not talked about at all, namely rank order filters. So a rank order filter, let me introduce it to you by example. Let's say if we are considering a 3x3 neighborhood. So these are, I'm showing here a raw image with a 3x3 neighborhood. For example, I can ask, what is the maximum value of these 9 pixels? Or I can ask, what is the minimum value of these 9 pixels? If you think of your gray value image as a surface, then this finds something like the upper and the lower envelope. Okay, so if I have some noisy image, for example, I'm now, if I'm using, this is now a one-dimensional example, okay? If I'm using a filter which is this large, and I'm now trying to find out what is the maximum, then let me try and do this correctly. The maximum will look like this. And so, I've used this distance, the size of my filter, and then I've grown at the same rate as my signal. And then because the signal went down, I just kept this maximum until I found the next slope and so on. And I hope you get the idea here from my picture. This is roughly, broadly speaking, this is what the maximum filter of this one-dimensional signal would look like. And the important parameter has been here the width of this maximum element. Of course, if I use a maximum element which is twice, or if I use a region of interest which is twice as wide, in this particular kind of research, this is called a structuring element. This filter mask is called structuring element. Of course, if I make it twice as wide, then I'm going to lose more details of my surface. And the minimum, just to complete this, the minimum would have looked something like this. So there's the maximum, there's the minimum, and then of course you can instead compute any quantile that you like. Yeah. So let's say I could use the 0.5 quantile. That would be the median filter, which is as you know, the median is a robust alternative to the mean. So, let's do this. Let's look at the median. The median within the structuring element would look something like the blue curve that I'm showing here. And now the interesting thing is, if my data has outliers, so if there's a spike in my original black curve, then of course the maximum filter will pick up this spike. The minimum filter, the red signal, will not see it at all. But the median, the blue one, will also be robust to that outlier. So if I had used a Gaussian smoothing, let me find a different color. A Gaussian smoothing would have been sensitive to this outlier. So compare the pink curve with the blue curve. The Gaussian is sensitive to outliers, but the median is not sensitive to outliers. That's an attractive property. So why did I spend so many weeks talking about linear filters? And why do I only talk about these fleetingly? An important reason is that these rank order filters are so much harder to characterize. So the linear filters, we saw that just knowing the impulse response, or equivalently, just knowing the transfer function, tells me everything I can possibly want to know about that filter. But with these rank order filters, it is impossible to, or it's much harder to characterize them in a data-independent fashion. Okay, so here I showed a 1D example. Of course, you can do this in 2 dimensions and 3 dimensions and so on. And so these rank order filters would allow you to span a morphological scale space. Yes?
Performance penalty?
You mean, are they computationally expensive?
Yeah, compared to linear filters are simpler to treat analytically, but in most cases you won't be interested in what your filter is theoretically able to do, but you're interested in what does it actually do in a finite amount of time.
So those are still pretty cheap operations. Yeah? So the finding the minimum and the maximum. So in the let's say, the minimum you can just find with a single pass over your data. Yeah? So you store
quantile is not that easy.
Okay, for the quantile, naively you need to sort your data. There are also quick sort type algorithms which allow you to find the quantile without sorting the full data set. Yeah? And anyway, there are often specialized algorithms as long as you only consider a few elements. So bottom line is, it's not as, if you need a really fast implementation, it's maybe not quite as trivial as just a linear filter, but it's not very expensive. Yeah? And by the way, these morphological filters, they are useful. So the morphological people, they call these operations erosion and dilation. Morphological people often only work with binary images, but these continuous gray values that we have here, of course, are a generalization thereof. Yeah? So here, this was my intensity or gray value. And these morphological filters, if we talk about binary images, they can be used, for example, to close small holes or to eliminate small bridges. Yeah? So you can do first an erosion and then a dilation, or vice versa. These operations are called opening and closing, and they allow you to filter out small holes or small islands in if you have binary images. And on gray value images like these, as you prefer, you can either become invariant to outliers, or you can particularly focus on these outliers in case you think that these hold interesting information. All right. So I just want to show you, that there's this space also. All of these rank order filters. Another type of nonlinear filter is a histogram. So, for example, I could compute, let's say, the response to a linear filter bank, and then I can make a histogram over a certain image patch of how often do I observe a response of a given magnitude. This would be a histogram that's centered on a single pixel, or there are also versions where, like this histogram of oriented gradients, where I can do that for a number of adjacent cells. And these histograms of oriented gradients have, for example, been used a lot in pedestrian recognition, or more generally to recognize relatively stiff objects. Pedestrians are stiff in that sense because, even though people move their arms and legs, it's still pretty well-defined posture that normal people have when they walk around on the streets. Okay, so there is this big space of what features you could possibly extract. The common idea is always to, have to associate it with every pixel in the image a set of numbers or a vector that should somehow encode the local appearance in the image. Any questions so far? And believe me, much engineering has gone into what is a good filter bank, compromise between speed and expressiveness and so on. Okay, then I want to talk about classifiers, and this is a sort of unofficial overview of what you could possibly do. So to learn this mapping from the features to the labels, when people started this business, they were quite interested in so-called generative classifiers, where in feature space you try and estimate a class density for each of your classes. Okay, so the typical picture that people will draw in machine learning lectures is a feature space with 2 dimensions, and then you have a couple of objects characterized by features that belong to the red class, a couple of objects that belong to the green class, and now we want to learn a decision rule. What you do in a generative classifier is that you try and estimate the density of the green class and the red class. In the case of linear discriminant analysis, you say, all right, I am fitting a Gaussian to the green class, I am fitting a Gaussian to the red class, and I require that these Gaussians have the same covariance matrix. So they obviously are allowed to have different means, but the shape of these Gaussians or the orientation of these Gaussians must be the same. And if you then do the math, and you now, given this fit to your observations, you try and figure out which class is locally dominant. If you do the math, you find that actually this results in a linear decision boundary. Yeah, so my decision boundary, it passed the point where the red and the green isocontours of same density where they met. Yeah? And given this linear classifier, we would say whenever we have a query, so if I have to make a prediction for this point, if it lies on this side of my decision boundary, I will call it the red class. If it lies on the other side, I will call it the green class. So this is a linear discriminant analysis. In quadratic discriminant analysis, you allow the Gaussians to be different. Yeah? So for example, I use this one, which is a nice fit to the green class, but I use that one, which is a nicer fit to the red class, and observe that they now no longer have the same shape. And if I now ask for the set of locations where these 2 Gaussians have the same density, this no longer is a straight line, but it is a curve which can be shown to be quadratic, a quadric. And in this case, for example, if we compare it to what the linear classifier would do, in these locations the red class wins, because in this direction here to this cross, the red Gaussian decays more slowly than the green one. Yeah, so I could draw you more isocontours, just to give you a visual proof, so to say. So now this is I'm showing the set of locations which have a distance, a Mahalanobis distance of 3 from the respective centers, and we see that in this direction here the red one decays more slowly than the green one, and hence I get out this curved decision surface that you see here. Why would you not always want to use quadratic discriminant analysis rather than linear? it looks like it's a better fit to the data. Why do you not always want the better fit to the data?
If you don't trust your data.
If you don't trust your data, yeah.
If you have some information that should be in your boundary.
Say it again.
If you have some other information that should be in your boundary, and you are reasonably certain that you violate the data that violates the boundary is only due to noise.
Okay, so nobody usually there's nobody telling me that my data is linearly, or that normally nobody tells me that the best classifier will be linear. Yeah? This would be a very fortunate situation. Of course, we often fit a linear classifier, even so. Can you give a more general argument? Yeah?
More complex models tend to overfit.
Exactly. So this is a more complex model. Broadly speaking, this has twice as many. So the quadratic discriminant analysis has twice as many parameters as the linear discriminant analysis. I'm cheating a little bit, yeah, but roughly. In the one case, I need to estimate the covariance matrix for one class. In the other case, I need to estimate two different covariance matrices. That means more parameters. And in the face of limited training data, I may not be able to determine these parameters reliably. And we have to remember that here I showed a two-dimensional feature space, but even in this simple example here, if we count the number of features I used here, it was 1, 2, 3, 4, 5, 6, 7, 8, 9. It was some 17 features or so that I used. Yeah? So really my points do not reside in a two-dimensional feature space, but in a 17-dimensional feature space, and a 17 by 17 covariance matrix. That's already quite a few that's already a substantial number of parameters. And if I return to this example, here I annotated a few dozen pixels. If I have annotated a few dozen pixels, but I have hundreds of parameters, that sounds like I'm going to overfit. So this is why sometimes it makes, or actually often it makes sense to use the simpler model just to avoid overfitting. Okay, this was the brief intro to generative models. Much more popular nowadays are discriminative models. At the heart of this is the idea that you should never solve a harder problem than you need to. So, for example, here I can argue that just finding the decision surface, or just to express what the decision surface should look like, requires much fewer parameters than actually fitting a density to both of the classes. So you can say, look, if ultimately my aim is to make the correct prediction, I don't care about the density of the classes. So I'm not even trying to solve that problem. Rather, I try to directly find the decision surface. And there are many methods for this. The first one I've jotted down here is logistic regression, which means you essentially fit a sigmoid to your data. It has a nice statistical justification of why this is the right thing to do in the framework of generalized linear models. Then, for a decade or more, support vector machines were all the rage. Support vector machines try to directly fit a linear decision boundary, which in some sense is as far away as possible from the members of both classes. Both of these methods also can be made nonlinear. In fact, I can always, from my existing features, I can always create new features. For example, if this was x1 and if this was x2, then I could create a new feature just from the information that I have, which is called x1 times x2. Yeah? Or I could take whatever, x1 times x2 squared, or whatever you prefer. For the example that I've showed here, this would not be very meaningful, because actually, you know, a linear decision boundary separates the two classes reasonably well. But I can, of course, you know, invent other examples like this one here, where the green class more or less surrounds the red class, where such additional nonlinear features can make sense. Yeah, so I can now lift my data set, which was originally two-dimensional. I can lift it to the third dimension simply by following this rule here. Yeah? I look up for each observation what is its x1 and x2 value. Then I compute x1 times x2 squared, and I translate my point by that amount in the third dimension. I do that for every training sample, and I find that generally when I embed my training data in a nonlinear fashion in a higher dimensional space, that generally this will lead to a problem that does become linearly separable. You can either do this really by inventing new features as nonlinear combinations of the old ones, as I have just given an example here, or you can compute you can invent a dissimilarity measure or a similarity measure between pairs of points. And if this similarity measure obeys certain properties, namely that the matrix of all similarity measures should be positive semi-definite, then you can also have the same effect without explicitly translating your points to this higher dimensional space. You can just work on these nonlinear similarity measures, and the effect will be the same as if you had, you know, inflated the dimensionality of your feature space. For the first few years when support vector machines were popular in computer vision, people went down this road. So they started with few features and then used nonlinear combinations of these, or they kernelized their algorithm. In the later years, the trend was to just extract more cheap features. So quite literally, in the case of image classification, so in the case of, that's the question, is there a dog in this image or not? People would literally extract 100,000 features from the image and then just train a linear support vector machine that decides, according to these 100,000 features, does it look like there's a dog or not in this space? Okay. Popular in a slightly different community is also Gaussian process classification. This can also be seen as a kernelized version of regression. Yes?
Is there some general cooking recipe how to get sensible features?
So the question was, is there a general recipe on how to get sensible features? And a yes and no. So on the one hand, you know, the coming up with the features or offering a set or a family of features to the algorithm from which the algorithm can then pick the ones it likes, this is always the responsibility of you, the designer. And the algorithm can always ever see the data through the glasses that you give the algorithm. Yeah? So if the features that you offer are just not informative, then the distribution in this feature space will not look like the one that I showed here, but you will have the following situation, namely that the red and the green class are completely interspersed. So nobody can fit a reasonable classifier to this. That's because the features were not informative. And yeah, you know, I can now lift this nonlinear to a higher dimension, I would be able to linearly separate my data in this higher dimension, but this would be a complete overfitting to the data. Yeah? So my resulting decision surface, would look like, this, and nobody in their right mind would trust this decision surface. Yeah? Okay, you get the idea. So you need to offer the right family of features to the algorithm, and the ones that I listed here, these are good candidates. Yeah? So depending on your computational budget, you would use a couple of smoothing filters, you would use a couple of filters that compute something like derivative or curvature of your image. You could compute lower and upper envelopes. So the ones that I've listed here are really the ones that many people have used and that they have reported good results with. That doesn't mean it's free of parameters. Yeah, you still need to say, what is the smallest and the biggest kernel size that you are using, but those are widely popular features. And altogether today, I'm always talking about a filter bank that the human supplies, and the classifier then picks the one or combines the ones that it likes. Starting next week, we will look at algorithms that really learn the filters themselves. Yeah, so all this neural network business. You have a question?
My question: to what extent do you pre-select features for a convolutional network, or give this into the network to learn it by themselves?
Okay, so the question was, what information do you need to feed into neural networks? It learns the coefficients of the filters, but you still need to specify, and that's crucial, what is the size of these filters. And that is a non-trivial. So the performance of your system can vary a lot depending on whether you make a good or a bad choice there. So when I'm saying that these filters or these features are learned, it's only partly true, because you still specify the family of features that can be learned in the first place. It's a large family, but it's not infinite. Yes, well, it is infinite, but it's not all conceivable features. Yes.
This is especially thinking about these examples for prompts, where you see that in the initial layers they usually end up learning edge detection filters, and this together with the fact that the earliest layers are training the roles, how to decide when to feed in the edge detection filter into the first layer and not have to learn this thing all over again.
So it's a valid question. Empirically, it's a little bit better. So empirically, it turns out that if you learn, even though it's just blob detectors or even though it's just edge detectors, if you learn them for a specific problem, performance tends to be a little bit better than if you had plugged general purpose ones in there. And the reason is that, a general purpose derivative filter is general purpose. And if you're interested in only, let's say, pedestrian detection, the set of images that you're going to look at is not, the complete set of every conceivable image in the world. And so you allow the system to specialize a bit more on the application domain, and that empirically pays off. It's not by a huge margin, but it is a bit better. Okay, good. So after the break, I will talk about a different class of discriminative classifiers, one that has many good properties. And then, in particular, I want to use the rest of today to talk about creative ways of using and abusing this architecture for computer vision. Okay. So the following This is a large family of algorithms which in its theory and justification is somewhat orthogonal to the previous ones. It is a class of algorithms that sounds, it does not sound much like first principles, but it works extremely well in practice. So, for example, this LDA QDA, there's a nice justification of why you would do that. There is some, a pretty nice theory behind logistic regression, Gaussian process classification, and the class of algorithms I'm talking about now. It's very much an engineered thing, but works well across a broad range of problems. And here is a brief summary of how that works. CARD is short for classification and regression trees. They're also called decision trees. And it works as follows. Here's our famous toy example. Here black versus red points. And the algorithm now suggests to iteratively partition feature space until the resulting nodes or until the resulting partitions or cells are pure, or at least close to pure. So here, for example, a first decision has already been made, namely if my observation is less than 1.49405, then I go left in my decision tree, and here I would predict that this is the black class, and on the right hand side, if I stop there, I would predict that this is the red class, and that's already not a bad classifier. By the way, in the most popular version of these classification and regression trees, these decisions or this partitioning of cells is always along splits that are orthogonal to one of the feature space axes. This is an arbitrary restriction. I could also decide to create a decision tree where my first split is like this, and then the second split is maybe like that, and so on. And people have tried that, and in certain applications that works better. So when there's a strong correlation in the input data, for example. But the most popular version does the following. It first tries out the first feature, and it tries out all splits and asks which of these splits is best in the sense of creating as pure partitions as possible on the one and on the other side. And then the best split that we found was, this one here. And then it also tries out the other axis. So, it tries out all these splits and sees which of these is best. And then it compares the best split that it found here, which will be maybe, that one, to the best split that it found for the other axis, which was this one. And then it chooses the better of the two greedily. Okay, and that's what has happened here. So the best split, the best axis orthogonal split that could be found on this data set was this one here. And this gives me the root of my decision tree. Now we look at the left partition, at the right partition. At the left partition, I think we're already done, because there are just black samples on the left, whereas there's still a mixture of black and red on the right. So we are now looking at this half space, and we're again trying out all these splits and recording which of these is best. And we're trying out all those splits and recording which of these is best. Well, and the one that did work best was that one here, which gives me, this was a root node, that now gives me a new node, a new internal node in my decision tree. So this time I'm asking if feature x2 is smaller or larger than 1.34071. Okay, and now we iterate this procedure until all leaves are pure. So one could formulate, this was a greedy algorithm, one could formulate an objective function that asks, what does the optimal decision tree look like for a given sample? Where optimal could be, for example, I want to use only axis orthogonal splits. They should be conditional on each other. So I want to have a tree. I could say that, for example, I want to find the tree with the smallest number of leaves that partitions my data perfectly. That's a valid question, but it is an NP-hard optimization problem, which doesn't mean impossible, it just means very, very expensive, and nobody ever does that. Yeah? So people just use this greedy algorithm. The advantage is that it's super fast. The advantage is that it has no bias, yeah? So it can fit or it can produce any decision boundary it likes. The disadvantage is that it has high variance. Yeah? So if, for example, if you give me a bunch of training data and I train one tree on the first half and I train another tree on the second half, the resulting decision boundaries are going to be somewhat similar, but the trees themselves are going to look completely different. Yeah? So the first tree we've seen here used the feature x1, but the second decision tree trained on the other half might start with the feature x2, and so on. Yeah? So this is called high variance. And and high variance, this is something undesirable. It means that your algorithm is not going to generalize very well. And to mitigate this high variance, it is possible to use not one tree, but an ensemble of trees, a forest. Now the trees, of course, there's no point in having an ensemble if all the members of the ensemble say the same thing. Yeah? So you need a diversity of opinions in order to have any benefit from having an ensemble in the first place. Okay, which means, for example, at work, there's no point in having meetings if the boss always knows what's right anyway, then there's, it's a waste of time to have everybody sit together in the same room, okay? So you want to have this diversity of opinions. And in random forest, this diversity is encouraged in two ways. First, you train multiple trees, but you only have one training set. So what you do is that each tree gets to see a different part of the training set. You sample randomly with replacement from your training set, so that each tree gets to see a somewhat different training set, and that already is enough, of course, to create different looking trees over which you can then average. In addition to that, it turns out to be beneficial to restrict the search for the best splitting position to a subset of all dimensions. Yeah, so if you remember that in reality we don't just have x1 and x2, but we have our 17 feature dimensions. If we allow a given node in the tree to completely exhaustively try out every split position along all 17 dimensions and then picking the one that it likes best, this will tend to overfit your data. So it turns out to be beneficial to assign only a random subset of features to each node, and the node, when it wants to make a split, can then only pick from this random subset. Incidentally, it also makes things faster, but in particular, it yields better prediction. Yeah? So here, for example, we see two bootstrap samples from the same training set and two trees that are trained, or a couple of trees that are trained from it. Same data set, different bootstrap samples, different resulting trees, and the results of all these trees are then averaged over, and that's it. So this results in a method that still has low bias, but now also has low variance. So while each single tree overfits, the ensemble will tend to overfit much less. And what is neat is that the method is relatively robust to if you throw many features at it. So if you're not sure which features are good in your data, you can just throw 100 features at it, and it will still give pretty good predictions. Also, it has almost no parameters, the whole thing. On the one hand, there is the number of trees in your ensemble. If you can afford it, then more is better. In theory, random forest can overfit if you give it, tens of thousands of trees. In practice, your computational budget is usually exhausted before you overfit in terms of number of trees. The other parameter, that's the more important one, is how many features does each node get to choose from. And there are some rules of thumb, like use the square root of all available features or something like that. And the good news is that the performance of the algorithm as a whole is pretty good and is pretty robust to the choice of these features, these parameters. In particular, it is less finicky than the SVM when you use a kernel. So if you use the nonlinear version of the support vector machine, your kernel has parameters, and the choice of these parameters can really very heavily impact your prediction accuracy. With random forest, there's really not all that much that you can do wrong. That's the good news. The bad news is that hand-designed features plus random forest does not give you as good performance as the neural networks that we will discuss in the following weeks. On the good side, it's much faster. So on a reasonably sized training set, a random forest can be trained in a matter of seconds, and with neural networks, it's a matter of hours or days. Well, let's say on the same size of training data, let's say minutes to hours. In any case, it's slower. Questions? Okay, so I come to the promised creative use of these algorithms. The first one is autocontext, and I just want to re-emphasize the point that the algorithm only gets to see the data through the glasses that you give to the algorithm. Okay, so for example, this is a pretty large window. These are maybe 20 by 30 pixels or something. And if you ask the classifier to predict what is this part of the image, and if you give it only filters which have access to 20 by 30 pixels, it may or may not succeed. So do you recognize what this is? Okay, I'm a bit relieved for pedagogical purposes. All right. Recognize this? Oh. Yes. Okay. He sees feet. That's correct. Everyone sees it, huh? So these are shoes, legs, and the thing behind. Car. Yeah, amazing, huh? We're pretty good, but we're pretty good when we have this much context. We all fail when we see that. Yeah? So we need more context. And if I now had used the program that you previously saw with the filters at the given scale on this image at this resolution and trained it to become a pedestrian detector, I would have failed, because the classifier only sees even less than that bit of context, and then how should it figure out that this is a person? Yeah? So the cheapest way to introduce context is the following, and this is, I believe, 2005 or so paper from Zhu and Tu. By the way, I think he's one of the unsung heroes of computer vision. You know, somebody who really, consistently makes some very nice contributions to the field. So that in his paper, from which I take this figure here, he tries to do a pixel level classification of which pixel shows a horse. Yeah? So this is the input, this is the desired output, this is the ground truth, and this is what we use to train the algorithm. Now, if we just use, a pixel and its local neighborhood, it's kind of difficult to decide, is this a horse pixel or not? And the result, by the way, if you train a method pretty much the way that I showed you interactively, you see the thing here in the background. This is the result. So it was actually pretty sure that, this is a part, this looked horseish to the algorithm. Also, the here the nose apparently looked a little horseish, but overall, it's been difficult. But what outer context now does is that after this first stage of classification, it takes all the original features, but in addition, it takes the output that you've just seen. Yeah? And uses all of that as input to a second stage classifier. And the second stage classifier, gives you output which is going to look better, and then you iterate this over a few times, and then I think this saturates after 4 or 5 iterations. In the end you get this, which is really not bad. Now you may wonder, what are these colored stars and so on? These are the particular features that he extracts from the probability map, but these particular features are not important. So what's important is the fundamental idea of using the classifier to produce a pixel level prediction, a semantic labeling, in this case horse or no horse, and to then use those predictions as input for a second layer of classification along with the original features. Here is my version of outer context made simple. Yeah? So we first run pixel classification using raw data and the features that we had decided to use. We get a prediction, and now we add this prediction as just a new feature to our set of features. And then we can, or if you prefer, we can, add the prediction or concatenate it to the raw data. Let's say this is the raw data, and this is the result from the classifier number 1. Let me call this out1. And now I can compute all my features, not just on the raw image, but on both images. Yeah, so I would get a structure tensor for my raw image, I would get a structure tensor for my prediction image, and so on. And then you train the next round of classifier with it, and you keep on going. The one thing to watch out for is that you should use different sets of labels for the different stages of your classifier to avoid overfitting. Any questions? Yeah.
So in this case, it looks like this training process is part of the technique to get the end result. But can I use now the filters that I get out from here and apply to the other picture of a horse?
Oh yeah. So so at each stage you train a classifier and you remember its parameters. And then, you can run the whole thing in feed-forward fashion at test time. Yes. More questions? All right. That's it already, yeah? It's not that hard, right? But it's a good idea, and you will, if you read papers, you find, this idea being reused over and over. Not least, by the way, you can argue that neural networks do the same thing. Yeah? Okay. Then another one of my favorite algorithms is this one here. So this was invented by Jürgen Gall and Viktor Lempitsky, and they first published it at CVPR 09. And here I'm showing screenshots from a PAMI paper they later wrote with additional authors. This one is interesting because if we go back to these images here, we had, after constructing the tree, each leaf of the tree held a collection of samples. And in this case, when we wanted to make a prediction, we simply looked at the label of those samples. So make a prediction means that we put I didn't really say explicitly how we make a prediction. So for example, if somebody asks me to make a prediction for this point here, if somebody asks me to make a prediction for this point in feature space, then I would start at the root node. I would ask, is its x1 coordinate larger or smaller than the threshold? It's larger, so I go right. Then I ask, is its coordinate larger or smaller? So this was the first split. Then I ask, is it larger or smaller than the second coordinate that I'm giving here? The answer is it's smaller, so I'm going this way. Then I'm asking, is it larger or smaller than that one? It's smaller, so I'm going this way. And then I'm asking, is it less or more than the next threshold? It's less. So I end up here. And then I look at all the training examples that live in this leaf. And if I've trained to purity, then all of them will be black or all of them will be red. In this case, all of them are black. So I predict that this point in feature space that I annotated here, this point in feature space I'm going to decide belongs to the black class. This is how I make predictions. But these were unstructured, so each leaf of the tree corresponds to one of these, partition elements of feature space, or to one of these cells in feature space, and each leaf of the tree, or each corresponding cell in this feature space, they only vote for a class, and that's it. Yeah? And Hough forest does more than that. So Hough forest does the following. Given, let's say, we are trying to detect cars. So we want to say where in the image is a car. So I can use a sliding window. So I can, extract an image patch this big from my image, and I do that. I'm showing here just a single patch from the image. Of course, I should do that for every patch of the image, and then I can decide not only if the center pixel looks like car or not. I should use a different color. So for this image patch that I've shown here, an unstructured prediction would be to just look at the center of the patch and ask the question, does it look like car or not? But if I want to predict where the center of the car is, which is what I need for detection, this is not enough. Huh? And by the way, given this image patch, so where would you say is the center of the car? We cannot really tell, but the center of the car, so we know that most cars have a front axis and a rear axis. We're not sure which of the two it is. but we can, estimate a little bit of perspective distortion here. So we probably think that the center of the car is either here or there. Would you agree? All right. This is precisely what the algorithm does. Yeah? So it takes an image patch at a time, and I said before that when we construct a decision tree, we always try and find a split in feature space which will reduce the impurity of the current node most, or which will yield two child nodes that are as pure as possible. And here we have two senses of purity, namely we have class purity and we have geometric purity. By class purity, I mean that ideally in a single leaf of my tree, let's say I want to train a car detector, in a single leaf of my tree, I would prefer either just patches that show part of a car or patches that do not show part of a car, but not both. That's what I mean by, that's the simpler notion. This is the class purity. And by the geometrical purity, I mean that, if I have some patches that think the car center is here, let's say these patches that think the car center is to the right, they agree geometrically, and then I have patches that think that the car center is left, and I would like these patches to end up in different leaf nodes of my tree. How can I achieve that? These authors do it by alternatingly using the two purity criteria. So when they want to split a node, they throw a dice to decide will they optimize geometric purity or will they optimize class purity, and then subject to this outcome, they then find the best split in feature space that reduces the impurity most. And they then end up with, for example, these image patches in a given leaf node. And these image patches, by the way, all think that, or almost all think that they are sitting on the left of the car center. So if I normalize by the car center, then they all think that they sit somewhere to the left and to the top of the car center. And this is kind of reasonable. Huh? We see rear view mirrors here, and the windshield is oriented this way. So the car center is going to be somewhere on the right of those patches. And by the way, the color here indicates red means it was really a car and blue means it was not a car. These are the members of a different partition or a different node of my decision tree. They show parts of wheels, and we see that here we have a nice purity in terms of class. They're all cars, they're all the red class, but we have a large geometric impurity, because some of these believe that they are the left wheel, and some of these believe that they show a right wheel. So if I now chose to split again this node, and if I cannot use the class purity as a criterion because it is already pure. If I use geometric purity, I would try and find a split that separates these two. And I think they've ordered the examples here in the correct fashion, so I would try and separate the front wheels from the rear wheels, essentially. Yes?
What is a good measure for geometric purity?
Okay, so I'm just looking at the green dots, and I'm computing, for example, their center of mass and their spread. Yeah? And if the spread is small, it's geometrically pure. If the spread is large, this is impure. Okay? So you fit the Gaussian to it, not because you believe that the Gaussian is a good fit, just to see how big is its standard deviation. Okay, and then you end up overall with something like this. So this is a complex figure, okay? So bear with me for a moment. The whole thing, this has already been trained, and now the whole thing is run in a sliding window fashion. Yeah? So I insert each patch, and the patches are even overlapping. I insert each patch into my decision tree and see in which node it ends up and what the members of this leaf node vote for. Now, if we concentrate, they didn't show the results for this because it's boring. So let's concentrate here on the red patch. The red patch is being sent down this decision tree, and the features, by the way, are very simple ones. So it's difference of intensities between pairs of pixels and so on. It eventually ends up in a leaf node, and in this leaf node, it finds patches. Here car patches were shown, but the same works for pedestrians. And now these image patches that are from the training data in the same leaf node, they will give you two pieces of information. One is they will vote for, is it the red or the green or the blue class? And secondly, they will vote for, each patch also has an opinion. If the patch thinks it is a car, or if the patch thinks it comes from a pedestrian, where is the center of that car or of that pedestrian? So the red sample ends up in a leaf of, or in multiple leaves because it's a whole forest. It finds exemplars there, and the exemplars both have an opinion what class they are, and secondly, they have an opinion of where the human, if it is a human, where the center of that human would be. And you see that some of these patches make bad predictions. Yeah, they say the center of the human is up there. Some make good predictions, but just looking at the red patch itself, well, it would say there is maybe something humanoid up here. Yeah. The blue patch turns out to be much more informative. So it's quite distinctive in terms of class, and all training exemplars which looked like this, or almost all, here's the blue patch, they thought that the center of the human must be somewhere on the top left, because we see this clear posture of this foot being raised. It's difficult to imagine the center could be anywhere else. So we get a pretty distinct blue class there. And now this happens for every patch in the whole image. And then these votes are being aggregated, as you see here. And then, you look for the distinct maxima in this space. By distinct, I mean that sometimes you have two maxima which are really close by, and then you use a greedy procedure. You start with the strongest maximum, and you say, this is a detection I believe in. You suppress all nearby maxima, and then you iterate over this because it could be that there are multiple humans in the image. Okay, so this is a very generic algorithm, very versatile, and before the advent of neural networks, this really produced state-of-the-art results in the detection of objects of intermediate complexity. Questions for the Hough forest? So I hope I did not confuse you with the colors here. So in this case, red and green and blue was just, to distinguish which patch we're talking about. Down here, the color actually meant, does it belong to the class of interest or not? It's questions, yeah? The question was, compared to neural networks, is it more interpretable? So it's a little bit like, once I have found a maximum, I could ask which exemplars voted for this maximum, and I could look at those exemplars. But the numbers of exemplars or of training patches will be very large. And so on the one hand, yes, the algorithm is pretty straightforward. I think I fully understand what it does. On the other hand, the same argument holds for the nearest neighbor classifier. The nearest neighbor classifier is also a very simple algorithm, but to reproduce its decision boundary, you need to look at all the training data it has ever seen, and that can be a substantial amount. So on one hand, yes, it's interpretable. This image here, it's pretty obvious. What's happening and what you should do. On the other hand, it's not a rule that you could express, in a single sentence, or it's not a rule which you could compress into 10 parameters. Yeah? It's a non-parametric method. Essentially, the number of parameters grows with the size of the training data, because it uses all the training data to make these predictions, or part of the training data to make these predictions. More questions? Okay. Yes?
How does the algorithm know where the center of the geometric center is?
Okay, good question. How does the algorithm know where the geometric center is? So you can train it with weak or strong supervision. Strong supervision would mean that you actually supply bounding boxes, and from the bounding box you can trivially compute where is the center. In that case, you would train the algorithm by saying that every patch within the bounding box, for example, shows a human. This is not true. Only some of the patches do. But the errors are just, or you hope that the errors are just going to average out. And even weaker supervision would be that you really only supply the centers of objects. Even stronger supervision would be that you give a full segmentation mask, so a detailed segmentation mask of the object. The bounding box seems to be a good compromise. More questions? Okay. So I have one more idea for you. Namely, you could maybe argue that this is already a variation on the previous idea. It's again turning a decision tree or random forest into something that makes structured predictions. On the top row, we see a couple of input images and the ground truth. So here, red means plain, green means grass, gray means sky, and black means no statement. In this example, green means grass, blue means cow, and so on. And somebody has been very patient here in annotating the bicycles. And the task is given an image to produce this semantic segmentation. So to say for every pixel which of the 20 or whatever classes were defined in this data set it belongs to. Now, if we train a pixel level classifier with all the right features, the result is not so bad. This is what's shown, or were these the textons? Let me see. Second row labeling. Okay, so these were pixel level predictions. I already find them surprisingly good. So somehow the classifier, by just looking at a little bit of brown cow, is able to figure out that yeah, this is actually cow. I think that's partially at least an artifact or a consequence of the fact that it's only 20 or so classes. Yeah? If we had 1,000 classes, by just looking at a brown patch, you couldn't tell, if this is a carpet or cow or what. Yeah. But these are the noisy single pixel classifications. What you can also do is you can let every node of the tree not just vote for a single pixel, but you can let each node vote for a patch labeling. And the way that works is that, again, you collect when you have when I want to predict what is this part of the image, I pass this patch down my decision tree. I end up in a leaf. In this leaf, it finds the company of maybe 100 or so patches from the training data. And each of these patches, because it was training data, has some labeling. Yeah? So for example, if this was training data, then this patch would believe that its top half is the blue class and its bottom half is the green class. But there's not just this patch, there's maybe 100 more patches in the same leaf. And now all these patches are, well, I cannot say averaged because the labels are categorical, so I cannot, average these numbers, it's meaningless, but I can pick for every pixel in the patch the class that is the most frequent. Yes? So let's say I have 100 patches, training patches. I look in each of my 100 training patches what class it predicts in the top left pixel, and the most frequent one is going to be my prediction. And the result of this is shown here. That's already quite a bit less noisy than the previous version. And now you can actually iterate this, and that gives you the result at the bottom, and that's not bad. And when I say iterate this, there is a second paper with some more details on this by the same authors. Essentially, so this is the raw image, this is the ground truth, this is the first, this is the pixel level prediction, and you see that inside this traffic sign there are still some errors. These are the patch level predictions where you first use this winner-take-all strategy for every pixel that I just described, and then given these resulting the resulting image, you can now for a given patch ask again what leaf it would end up in, and you can use that to estimate a new labeling, and you iterate this until finally you have deleted this this hole in your, or this error in your segmentation result. Okay, so a bottom line here is to take a patch as input, but also give a whole patch as output, to do that multiple times, and then reconcile the result over your over the individual trees in your ensemble. Any questions for that? Okay, so if I consider these ideas, the auto context and the structure output, as basis vectors, then there are dozens of nice papers that then use smart combinations of these basic ideas. So fundamentally, what we talked about today was semantic labeling or classification at the pixel level. The approach we used or discussed today was that of a human supplying a set, possibly very large set of features, And we saw what these features could be. They could come from linear or from different kinds of nonlinear filter banks. I gave you a very rough overview of what classes of classifiers are out there, and I explained in a little more detail classification trees and random forests, because they are a nice compromise of speed and robustness and ease of use. And I showed in the end a couple of creative derivatives of these random forests and how they can be used to leverage image context, which we need if we want to go beyond this and understand that, yes, these were legs and there's probably a human body center a bit further up. Thank you very much.